Pretty good. Yeah,
You have
looks
two
good.
projectors and three TVs.
Okay, it should be enough for a small room like this. For sure is enough. Okay, good. But I'm frozen, am I?
Yes, like it's still upcoming.
No, no, yeah, it's just a delay. Let me stand up to see how well I... I think it is nice, it's good. Like, what direction I should go to make myself more visible?
Everything is fine, but like it's
Maybe you can lift it a little bit. Yeah, to show my upper body only.
okay. Should it go left?
Me left? Or you move that to left?
No, like you said that.
Okay,
I believe that it's fine. Right?
I think it is fine too.
Okay.
It's gonna be fine. Okay, all right, guys. I think we're good to go, right?
So grab a cup of coffee and I will talk. It's okay.
So you're gonna come back?
Yes.
You don't need to come back. You can come.
Because I have to grade them. Like I have to know that what are the questions and what are the answers every time.
So you need to know the answer. So
Because
those questions.
I am the one who is going to grade them, give them grade. You know the corrections in the exam.
Exam. Oh, so I still don't understand. So you need to give this like a link that they can reserve this.
Like I have to go through this lecture again to give them the marks
Marks.
for the exam, for the midterm exam. Like
Okay, I got it.
So-
Okay, you can follow this in your room or you can come here. Up to you. Up to you. Okay, guys, you know what that is? This is our team sign. This means respect. Respect. Why we need respect? We need respect because the matters we're going to discuss today are respectful. These are something that is a little hard to understand, but with our can-do attitude, we can make things to happen. Here's what I would like to do. This week, we're going to go fast with these three-dimensional matters that is left to be discussed. And next week, I would like to make a little bit of special week, and I need your collaboration. I need your cooperation. And next week, in the beginning of my lecture, I would like to do something a little different than what the course is about. And something a little different is me give you the presentation about the research proposal that is very important to me. There is this call that is called ERC, which is organized by it's a European Research Council funding that is, it's something that is extremely hard to get. And this is a call that there's like two steps. First you're submitting the proposal, full proposal, but there's a part of the proposal which is 6 pages only. And based on 6 pages, they will select the candidates for interviews. And then the next one is like there is a more detailed proposal and interview. And I was selected to interviews. And I would like to get started these interviews with you guys. So I'm going to keep my 5 minutes talk. So they say that I'm allowed to use 5 minutes to introduce my my project is about. And then what I would like to do this 5 minutes, and then what I would like you to do is that why don't you give me the criticism about my appearance, my presentation, everything you like, everything that you feel that is off, everything that you don't like. And each of the criticism is worth of 1 point in in-class quizzes. So if you say, hey, otherwise it's good, but I don't know about your shirt. Is that really your best shirt? Can you get any better than that? What about your physical appearance? Can you make your looks more sporty? Stuff like that. And then you can also criticize the content, the content of the presentation. Yeah, I was unable to understand this and that, so that wasn't that clear. So what exactly you would like to say here? And what about your missing enthusiasm? So do you have enthusiasm at all? This is something that I'm going to get started. My actual interview will be on March 18. So it's not going to be any time soon, but this is the time that I start preparing myself for that. Because now I know the rules, I know the length of my presentations and so on and so forth. So you guys want to play with me? Okay, good. And it's not going to be, of course, you will be awarded because you can get these points if you do something, if you say something. You can say anything you want. Quality of the content but I would like to get them more about your views because you guys younger than me. So let's say that I'm more experienced than you, but that means in English it's older than you. So maybe there's something in my appearance that is not good. Okay, so that's next week. This week, we're going to close the discussion about three-dimensional multi-body dynamics. That's where we're going to close the case. And I think if everything goes as I plan, we actually have a time to start about the introduction of flexible bodies. And it's going to be just, a little bit of warming up. And then the real deal will be when we're jumping into the finite element method. Finite element method that I do know that you are aware of the method, but I would like to explain the method differently that you have used to deal with. Because I know that you have learned the method that there's these like nodes, and then between the nodes there are springs. And that's not the way that I would like to introduce the finite element method, but something different. What is this something different? We get back to that. If not today, it's going to be next week. And then, like mentioned here, week 6 is a little bit of inconvenient timing because then we're going to get the visiting lecture about the biomechanics. That's exactly in the middle of story of flexible multi-body dynamics and finite element method and so on and so forth. But time-wise, that was the only possible week available. So I need to apologize that. All right. Then Mustafa mentioned something about this exam. So this midterm exam. He's going to get back to you regarding the details momentarily. But soon we have a link ready. Yeah, because we need to offer a link some kind which includes a question bank and so on and so forth. So that's going to be momentarily ready. So then you can enroll to wherever you wanted to do your exam. So the options are here or any other university. I think even Applied universities might have this kind of exam location. They might. This is something that I'm not really familiar with. All right. So 3D multi-body. 3D, this is not even that much multi-body, but it's kinematics. Three-dimensional kinematics. Okay. But before that, let's look what we discussed a week ago. So a week ago we discussed about, sorry that these screens are a little bit inconveniently located. Here's one screen. That seems to work. What about that? Is there something there too? That's okay too. Okay, so we discussed about how is it we can describe a particle in spatial applications, in three-dimensional space. And we learned that we want to use something that is a body reference coordinate system that is attached to the body. So it's welded to the body. So it cannot move regardless of the case. So if the body moves, the body reference coordinate will do the same. If body rotates, body reference coordinate system will do the same. So they are inseparable. So they are same thing. They are completely attached, rigidly attached. And when we kind of make a use of this body reference coordinate system, it simplifies the description of particle within the boundaries of the body. Because within the boundaries of the body, we're going to use something that is vector u bar that is constant. Because these particles are unable to move relatively with respect to each other. Now that's simply because we are assuming body to be rigid. And that's where the assumption is coming from. All right, so we first need to describe where the body reference coordinate system is located at, and that's going to be described by using vector r. And then we need to take its orientation into account, and that's going to be something that is described by using this 3x3 rotation matrix. 3x3 rotation matrix that is seemingly simple, but in theory is very hard to understand, hard to deal with. And we have, roughly speaking, we have two alternatives. We can describe the 3x3 rotation matrix using 3 parameters, like Euler angles. And Euler angles, there's many varieties how you can do the sequence of rotations. Regardless of your choice, you always have difficulty that is called singularity. Singularity is inability to differentiate what rotation is what. So sometimes what happens when you're using 3 rotational parameters, this rotational axis becomes to be parallel. And that's when you're losing your opportunity to see what rotation is what. And that is called locking, even though that is not physical lock, but it's an inability to understand what is what. That's what it is. And that happens always when you're using 3 parameters. There is no way to avoid it. Okay, let me, okay, no way to avoid it is a little bit hard way to say it because there's something that is a recent developments in kinematics, which is called Lie group. Lie group is something that for sure you haven't heard about it. And even when you're going to doctoral studies, you're probably not going to touch to that. But that's the new development that is taking place. And there's many scientists that are very excited about the Lie group. And why is that? Because Lie group is based on 3 parameters, and it can avoid the singularity. But that's something that we are not going to touch in this class, because the Lie group studies are still underway. They are not completed. They might introduce some computational efficiencies, or they might not. This is something that is unclear at this time. Okay, but I think that they will, because there is a big promise in the Lie group. And Lie group is entirely own mathematical discipline, which I recommend you not to familiarize yourself this time. You will have plenty of time to do that later, but for your information. Okay, so 3 parameters problem. How we can fix it? Using 4 parameters. So that's a kind of like against the common sense. They're a little bit against the engineering sense, because if you have a problem, you're increasing the parameters to fix the problem. So what happens when you introduce the 4 parameters? Then the singularity is no longer a problem. But understanding what these 4 parameters are standing for, how is their physical interpretation, that becomes a bit difficult, because a body can rotate in 3 different ways, not in 4 different ways. So these parameters are not free to move as they want. They are combined. They are constrained. And the way they are constrained is that there is a constraint equation involved, which simultaneously needs to be taken into account. Okay, that's a lengthy story. But what I wanted to tell you today is this. I don't have my pen with me today. No, it's because it's in my backpack, and my backpack is, guess where? My home. My home. Okay, what about what if I use this pen? Not good. This pen is not very good. Okay. All right, so let me explain something more here. So what's going to be the consequence of this 3 parameters, 4 parameters business? This is going to be serious consequences in computing. And consequence is this. You know, in kinematics, we need to deal with the angles. We need to deal with angular velocities, and we need to deal with angular accelerations. So those are the things we need to deal with. And things becomes to be complicated when we look at the angular velocities, because angular velocities is clear quantity that consists of 3 parameters. So there's angular velocity with respect to body reference coordinate system or global coordinate system. So it consists of 3 parameters. Now when you're using these rotational parameters, their time derivative is different than angular velocity. Now, if you hear me like velocity different, that's okay. I don't expect you to understand what I just said, but it's like the real reason why this is a big deal. I'm going to put it in writing here, so online participants can see this, but I'm saying that if you have 3 parameters, this is your vector, help me, so it was C, phi, like I say, theta, and psi.
Yes.
What was the sign of this? Was it like this?
No, like trident.
Oh, yeah. Like this?
Yes.
Okay. So these are the rotational parameters. I'm going to get back to the online participant. If you differentiate this, you will get C dot. Phi dot. Theta dot. And psi dot. Like I said. Okay. This is different than this vector, which is, it doesn't matter how you do it. You can do this using body reference coordinate system, or you can do this by using global coordinate system. This is not dot here. They are not same. They are not same. And that's the source of the problem. They cannot be same. I mean, if you can find a way that they are same, please come and inform me. You can say, okay, collect your stuff and leave. I'm going to take over your office, and then we all together, we're going to go to rector's office. Rector going to give you a doctor degree, and then a lot of other fame and everything. Professorship like same day, if you're able to find it. The way to do it. I think it is going to be hard, but why don't you give an effort? You never know. Maybe. Okay, now. All right, so here's 3 parameters. So Euler angles is one way to go. It's based on successive rotations. That's what it is. So one rotation after another rotation. That's what it is. Okay, then the method based on 4 parameters. The good example is this Rodriguez equation. And Rodriguez equation is based on 2 vectors. The one that is a vector that you wanted to rotate. This is what you wanted to rotate. And to make a rotation to take a place, you can introduce a assisting vector that is unit in a length. And because this is unit in a length, unity is here the constraint. Because these vector v parameters cannot be selected randomly, but they have to be unit in a length. All right, so then you're welding these 2 vectors together like this, and then you need to introduce a rotation amount of theta. And then after heavy mathematical manipulation, you are able to express 3x3 rotation matrix that consists of 4 parameters. 3 parameters because of vector, unit vector v, and 1 parameter because angle theta. And we use the skew symmetric form, which is an alternative for cross product. Skew symmetric form is a little bit more pleasant in terms of matrix manipulation, in terms of mathematical manipulation. Okay, the skew symmetric form is nothing too special. So there it is. Here is our 3x3 rotation matrix and the constraint that need to be fulfilled. It's kind of funny story that some 25 years back when we made the first code in multi-body system dynamics, we decided to use this Rodriguez equation. Actually, we decided to use Euler parameters, excuse me. And what we were missing at the time was this constraint. And each of the bodies were behaving really weird way. So we started like simple pendulum. And then when the pendulum started to rotate, its length becomes to be much longer than initially. And we were like, oh my God, did we invent it that this is a flexible body? No, we didn't. So it was just a mistake in a code, and the mistake that was there was a missing constraint. Constraint wasn't there. All right, so here's my first in-class quiz. In Rodriguez equation, rotation is described by 4 parameters. And these 4 parameters are coupled because of angle theta is small, vector v is unit in a length. We are assuming the body to be rigid. Parameters are not coupled because body can rotate in 4 different ways. And this in-class quiz is open. So, by the way, I see that there is a mistake because the room is LUT2, not LUT, but LUT2. So please log in using your student ID number and enter your answer. And I'm going to revisit this. And if you look at this, this is exactly the same that I asked a week ago. No difference whatsoever. So if your memory is good, you're going to be fine. Okay, and you guys have now this WhatsApp group, or you don't? You still don't? Are you sure that there's no WhatsApp group? Because what about Team Finland? Do we have a WhatsApp group here in this class? No.
I think there is a WhatsApp group, but there is no quiz there at the moment.
Okay, so it's not active. Okay, so I'm going to get back to this. So are you able to enter your answer? Again, LUT2 is your room number, and use your student ID number to log in. I will get back to this momentarily. Let me continue my story. I can continue my story. Okay. All right. Next is another way of describing rotation, which is called Euler parameters. Is almost like the same than Rodriguez equation. It's just a name, or let's say the title game here, name game almost. So we want to call the different parameters by different names, and this is going to give us something that is called Euler parameters. And now what is seemingly close to each other is Euler angles and Euler parameters, because the name Euler. But actually, these 2 methods has nothing whatsoever to do with each other. I mean, there is, of course, a link that you can build from one method to another, but conceptually, they are very different because one is based on 3 parameters, that's Euler angles. Another one is based on 4 parameters, which is Euler parameters. So they are conceptually very, very different. Now, Euler parameters goes in such a way that we can substitute this, and again, I don't have my pen with me today, this trigonometric relation to this 4x4 matrix. Once do so, 4x4 matrix can be written like that. And then what I'm going to do is that I will start calling these components by certain names. And those names will be Euler parameters. So that's a trick that I'm doing here. Okay, so here's, upper right corner of my slide, you can see the 3x3 matrix. And then I start calling, okay, theta 0, it's going to be cosine theta divided by 2. That's my first name. Second name is going to be theta 1 is going to be equal V1 multiplied by sine theta divided by 2. Another name. Third one is going to be V2 sine theta divided by 2. And then finally, obviously, it's going to be theta 3 is going to be V3 multiplied by sine theta divided by 2. Now, once using this name game and once substituting these names to my 3x3 rotation matrix located again upper right corner of my slide, I'm going to have matrix that is put in the writing here in the below. No trick. Name game. Nothing but the name game. That's how it is. Now, again, 4 parameters, so I still have to have a constraint some kind. I cannot select these 4 parameters as I want. And that's obvious because remember what's behind of these names. Behind of these names is still our good friend, vector v. It's still there. Because if you look behind the scheme, if you look at behind the names, the components of v is still there. So the v still need to be unit in length. So that's going to be our constraint. But this time, we're going to express this a little bit of different ways. So we're going to say these parameters, vector of length of the vector of these parameters need to be unit in a length. That's our constraint. So that's a simple game. Okay, so that's another way to express the rotations. Okay, any comments, questions so far? How it sounds? It's like, okay, pretty okay. Okay, so we went this fast, but I think that you need to just memorize the concepts, nothing but the concept. And next time when somebody is coming to say that, okay, I'm going to describe the bodies by using 4 rotational parameters, don't say, you're wrong, because body can rotate in 3 different ways, because that's what is being often used. In practice, most of the modern engines, if not all, are based on 4 parameters. I mean, all these commercial software, they are based on 4 parameters because they are mathematically so pleasant. But what's being made too is that there is a link between the 3 parameters and 4 parameters, and usually is in a post-processing and pre-processing state of the software. So when you're building the models, typically the software is allowing you to use 3 parameters because humans are so much better in 3 parameters than they are for 4 parameters. So once you put your body in a right kind of configuration, once you introduce the initial angles and so on and so forth, before the computing is actually getting started, there's a conversion behind. And conversion goes from 3 to 4. And then the computing will get started. Because computation is going to be so much more pleasant with the 4 parameters. Once response is computed, you want to display the results to user, you go back to 3 parameters. That's very, very common. And again, in computer graphics, quaternions, Euler parameters, very, very often used. So that's more about your information. Now, the next section is going to be very rapid, so we are not going to spend too much time here. This is what we learned already. Last course that transpose of the rotation matrix, it's inverse as well. And that's simply because rotation matrix is an orthogonal matrix. It's an orthogonal matrix because if you look at the columns of the rotation matrix, the columns consist of angles of coordinate system. Excuse me, the axis of the coordinate systems. And these axes in a coordinate system in three-dimensional space, they are perpendicular with respect to each other. And that's a definition of orthogonality. And they're also unit in length. That's not necessarily required, but orthogonality comes because they are having the direction where they are perpendicular with respect to each other. Okay, so that's orthogonality. And because orthogonality, transpose is same than inverse. And you can do the test by changing the order to be revised. So if you first rotate the vector v like this, you can rotate it back. You notice that the only difference is transpose. So that's it. Okay. Then something that is, because of this orthogonality, matrix multiplied by its transpose is going to be identity matrix. An identity matrix is something that diagonal components, this time 3 by 3 matrix, diagonals are as ones, is going to take a place. And the three-dimensional space, the order of rotation, you cannot change. You just cannot. Planar case, you can't because there's only one rotation, one way the rotation can take place. But here, you cannot change the order. Good to keep in mind. Okay, let's discuss shortly about the robot kinematics, and then we're going to move on to something a little different. Any comments so far? All clear? How come I have a little bit of a hard time to believe that? But you say no questions. Maybe not clear, but no questions this time. Would that be better interpretation of your face? Okay, what about this? I know that is I think it is a university rule that you're not allowed to commute. You're not allowed to interact with during the lecture. But what about this? So if it is clear, you do like this. If not so clear, do this. If you're very confused, is this. So which one it is? You're confused. Okay, so you're okay. It's okay. Everything seems to make sense. All right. Okay, robot kinematics. Here are the questions. How the 4x4 matrix presentation can be used in robot kinematics. This is pretty much what I would like you to be aware of. This is something that is standard procedure in robotics. You might have already heard about it. Might. Because those of you that have taken any classes in robotics, usually these classes are getting started by explaining the kinematics. And the kinematics goes by 4x4 transformation matrix that explains the kinematics of any robotic systems. And I wanted to explain you how that is related what we have learned so far. What's the difference between what we have learned and the 4x4 matrix, and they're not different really. So there's a little bit of like name game again, and then we're going to use something that is Denovitt-Hartenbach, which is the most often used 4x4 transformation matrix method, based on 4 parameters. And once knowing these 4 parameters, you can create the kinematics automatically. This is very, very straightforward way to build the kinematic relations. But again, it's a kinematics only, not dynamics. And remember, kinematic is the art of motion. It's not about forces. It's about how things are moving. Okay. All right. So then 4x4 matrix. So this is a typical robotic system consisting of several different arms. And what we can do in these arms is that we can move from one angle to another by multiplying these 3x3 matrices. This is how we can travel. One thing that is not accounted, if you just use a rotation matrix, which is 3x3, is what about the length of the body? You don't know. You actually know what is the orientation of end effector. End effector is a end of the robotic arm. So where you do the gripping or grasping or whatever you wanted to do with your robotic system, you know its orientation, but you don't know its location. And of course, you need to know it both. Otherwise, you cannot really make use of this information. Okay, so with multiplying 3x3 matrices, we know its orientation, but we need a little bit more. And that's where the 4x4 transformation matrix method comes into play, and it can take the translation into account similarly, like we're moving from one rotation to another, from root to the end. The same way, we just take the translation into account. All right, robotic system. So one observation is important to do. Robotic systems are having a little bit of different problems than anything else we have discussed so far. And it's a little different because typically what we wanted to know in a robotic system is that what is the length? What is that where the body reference coordinate system should be transformed in terms of reference coordinate system, and what's its orientation supposed to be to reach the certain place. Because the robotics is all about, okay, I want to touch this point. Let's say that I have here a fixed point and I want to touch end of the pen. This is what I wanted to do. I want to touch with this configuration, with this location. This is what I wanted to do. Tell me, how can I make things to happen? How can I make things to happen? I need to know the angles of each of my joints to do this, to make things to happen. And not just to touch it once, but often there's a trajectory, some kind of like a path that you need to follow. How you can follow this path, the one that I'm just doing with my finger, by adjusting these joints in my arm. This is very natural for a human. Very complicated thing for robotic system for one reason. And the one reason is redundancy. So redundancy is the fact that I can actually put this, or I can put my finger in this configuration by using multiple different angle configuration. Look at this. It stays in same orientation, same place, and I'm changing my angles. When I have a trajectory, I can do it naturally. But in a robotic system, easily happens is that you started to do like funny ways. You started to move the angles because it's possible. You can solve it by using multiple possible configurations. And this is called redundancy because of multiple different ways. Now, this path planning, trajectory planning, there's a lot of algorithms available. They're often based like, okay, don't start to play with other angles than necessary that you need to play with. There's a lot of information out there, but this is something that is good to keep in mind. That's what they wanted to solve in a robot kinematics. Okay, now we use this equation, translation plus rotation. That is not very good if we have the robotic system because we would like to combine it. So, how to combine it? That's straightforward. So let's just reorganize the components that actually matters here. The components that matters are, of course, 3x3 rotation matrix and translation of vector that is described by using vector R. Those are the components that matters. Okay? Let's do it in a way that let's just take it, no thinking needed. Let's just take these two components and substitute them to matrix that is 4x4 transformation matrix. So rotation matrix, first of all, will be located at upper left corner of my 3x3 matrix. So it occupies first three columns, first three rows. That's what it's taking away. What is left is one entire row and one entire column. Already others are occupied. Then I'm going to take my vector R. I'm going to locate my vector R to be in the upper right corner of my 4x4 transformation matrix. So now what is left is going to be one single row. One single row is needed to match the dimension. So let me fill that by zeros, except the diagonal component that is the last component of that row. I'm going to put that to be 1. That sometimes is called like scaling factor, which I don't understand why the scaling is needed, because scaling is not really needed here. And what that is doing is exactly the scaling. So if you put any other number than 1, it's going to make things to be bigger or smaller, but I don't understand what could be the reason to do so. Okay, this representation is called 4x4 matrix representation, used in robotics very extensively, very often. How it works? It works in a similar way that our kinematics works in the first place. So you need to build a vector that is like within this new frame, the frame that has translated and rotated. Now you're describing where you want to go within this frame, and this can be described by using vector B. Vector P consists of a total of 4 components. And these 4 components are components of vector U bar plus, again, 1 to match the dimension. Now you do the multiplication, you find your way to wherever you want it to go. Just checking if people are still alive. The online participants are saying that I'm frozen. Are they?
Like, there's one comment and I don't know whether they are really students or not.
Okay, so that's a nasty comment.
Ah,
You know, sometimes there are these, they are selling stuff and they use it. Remember, this was a bigger problem a couple of years back. They were sending links like, click this. Once you click that, it took all your money away. Not exactly like that, but it was like, okay, now the next thing we need is your bank account information and so on and so forth. So you need to be careful with these scams, if there is a scams. You think it might?
no, like, the question is a little bit curious, like asking some, like whether anyone from India or not in the middle of the lecture.
Okay, all right, so anyone from the India. Okay, but not asking my bank account number.
No.
Okay, so then, all right. Okay, that's where we are. Okay, I know that I feel the pain. I feel the pain, like the way you do as well. This is not what I promised. I promised that come this class, there's going to be a lot of laughing, a lot of enjoy, a lot of happiness. Where's the laughing? Where's the happiness? Where's the fun? Where that is here? Where it is? Where is it? You promised a lot of fun. And now it's all about, this, parcel, this. No parcel, but kinematics, that is a big pain. Is it that you shouldn't trust me? Yes, you should trust me. But let's go from the little bit of hard way. Let's take a little bit of jump from the bottom to go up. So momentarily it's going to be something more practical. This is practical too, because if you want to create kinematics, this is a beautiful, beautiful way to make things to happen. But things will be better. Trust me. Okay. Let me guess. No comments, questions? No. Okay.
What is the benefit from using this Borders focus? Now it just adds the 1 at the end to
Yep.
their eye.
So what's a big benefit of this? Yeah, that's a fantastic question. And thanks God we have Mustafa here, because without Mustafa I probably would go back row and hug you. But Mustafa is here, a bodyguard. If I do something stupid, he's always, okay, stay there, stay there. It's a beautiful, beautiful question, and it's because of this. If you really want to know where the end effector is located at, you need to know 2 things, translation and rotation. And now we saw that, okay, if you know the rotation, you know that how is the orientation of the end effector. That's not enough. So we need to know also where that is located at. It's orientation and location. And now when we do this combination, that gives us automatically. And now what we're going to do is this. Instead of using this rotation matrix, we can use a transformation matrices for each of these joints. And once we do that, then we know location and orientation of end effector. That's what it's doing for us. So it's actually giving us the kinematics as a whole. These kinematics can be used in other purposes too. You can use the kinematics to figure out the singularity configuration. I mean, that's a real singularity configuration. Like if there is a possibility that your mechanism can get locked, your kinematics will tell that to you. And that's going to be based on this 4x4 transformation matrix. Nice question. Okay, let me explain this a bit further, and then I will get back to you. Now, here's an example. This is pretty much the same example we did by using multi-body approach. Okay, we have body B here that is rotated 30 degrees with respect to global coordinate axis Z. And this is the only rotation that took place. Coordinate B is also translated 10 units along the x-axis and 5 units along the y-axis. Tell me where this one point is located at, and I can figure that out by first creating these 3x3 rotation matrix. then take a translation into account, and then forming P vector. Sorry that I don't have my pen with me today, so I cannot really highlight it, what is what. I can try. So Mustafa, tell me if it's going to be not looking good anymore. So, okay, so, no. This is not good. Okay. No, I just cannot do the drawing today. Yeah, not possible today. Sorry about that. And you don't see that well anymore, so I realize that too. Okay, let me take it back. Now let me take it here. What? All right, we are back here. So I cannot make a drawing, but let me use my mouse to explain this to you. So what we did in this numerical example was this. So we took this rotation matrix, we place it here, okay? Then we use this translation, we place it here, and then we build the vector U bar, and this is telling us the final location, okay? Orientation we know already because we know how it is rotated. And here comes this magic thing. So now what we can do with help of these 4x4 matrices is that we can move from one body to another by multiplying these 4x4 matrices together. So let me correct, each of the arms, each of the bodies of the robotic system will be described by one 4x4 matrix. You keep on multiplying these matrices together so you can move from one body to another, and third, and fourth, and fifth, and so on and so forth until you reach the end. And now once you do the multiplication, this tells you automatically where the end effector is located and what is its orientation. That's what the kinematic is about. Now that's the beauty of the method. So it's a kinematic description of not just a single body, but entire robotic system. And this becomes to be even more useful when we're using the method that is called Dynamit-Hartenberg. Because here, problem is that we are assuming that one body versus another body can translate and rotate can translate it in three different ways, and it can rotate in three different ways. So there's a total of 6 degrees of freedom. And that's not the case in robotics. They can move with respect to neighboring bodies in a certain way only because of the constraints, because of the joints. And that, because of the limiting motion possibilities, this becomes to be very useful. Make sense? Okay, so here it is. So this was a 4x4 method. And now I'm about to explain you this method that was called Dynamit-Hartenberg. And Dynamit-Hartenberg is method where we are not taking all possible translations and all possible rotations into account, but limited. Actually, this is a method that consists of 4 parameters. 4 parameters only. And 4 parameters you can create for each of the robotic systems. And once you do that, your kinematics is done. So it's automated ways to create the kinematics. That's what it is. And now if you differentiate your kinematics with respect to your angles, and you can do that by using a symbolic math tool, you can figure out the singularity configuration. So all that becomes to be quite handy. Okay, now, 4 parameters, because we need to look at what are the typical joints between the bodies, and it's going to go such the way that we are dealing with the limited number of joints. We're dealing with the cylindrical joints, revolve joint, and translational joint. Those are the things we're going to deal with. And of course, we need to take the body length and possible twist into account. And each of these matters can be accounted by using 4 parameters that are like this. Okay, so it's not so easy to read some of the figures are not clear, but I hope you understand. The first parameter is a length of the body, measured for the normal of z axis. So this is the kind of the length of the single arm, how long it is. And it's called A. Second one is alpha. And alpha is how much these are twisted. So if they are having if you have this kind of the arm, so the length is going to be A. And if the rotation, if the orientation of this end and this end are same, alpha is going to be 0. If they are 90 degrees, it's going to be something else, and so on and so forth. So that's what it is about. Okay? 2 more parameters are missing. 2 more parameters are distance from revolute joint perspective from one joint to another. And this is something that if you look at this figure here, which I'm unable to draw it, but let me use my mouse here, is about this D. How much they are separated like this. So this is going to be D parameter, and the last parameter is going to be angle theta. How much they are having the angular difference in original configuration. These are my 4 parameters. And these 4 parameters, what I'm going to do next is I'm going to create 4x4 transformation matrix for each of these parameters by using substitution technique, nothing but substitution. I'm going to take my Euler angles, and I'm going to substitute this information to Euler angles, and it's going to give me 4 different 4x4 matrices. Once I multiply them together, that's my kinematics. Okay, first one. Parameters is this. So I'm using multi-body interpretation here. I'm saying the length of the body, so obviously is a translation with respect to Rx direction. Once I substitute that information to my 4x4 matrix, this is how it looks. Each other, all the other parameters are zeros. And I will do the same, but angle. Now this is a one angle that is for my Euler angles, going to be angle theta. Look at that, how beautifully I pronounce my angle theta. So it's going to be angle theta, it's going to be equal to that angle alpha. Nothing, all others again are equal to zeros. Once I do that, this is how the 4x4 matrix look like. And then the distance D. The distance D is going to be this one here, the last component here. It's going to be located here. Last one is, again, rotation. And this rotation is, is angle, it's going to be angle T. T. Correct.
Yes.
Correct. That's what it is. And now this time angle C is going to be called angle theta, using your name tags we just introduced. And again, you get this 4x4 matrix, only thing left. Multiply them together, so then we can take each of these motion possibilities into account. Once you do it, this is how your method look like. So this is a 4x4 matrix, consists of 4 parameters. How it works? It works like this. You take your robotic system, you're going to keep these 4 parameters, each of the robotic arms, just put it in a table, and once your table is ready, then the kinematics will be created automatically. That's how it works. So automated ways of describing the robot kinematic system. Okay, so let me practice. So here is a not too complicated robotic system. And by the way, the beauty of this method is that it's spatial method. So it takes 3-dimensional rotations into account. Oh yeah, I see this, I see this. Okay, what you guys say? Should we have a very small break? Would that be okay? Because I'm a little bit in a hurry right after this lecture. I need to go and have my lunch. And that's a big deal, of course. Not highlight of my day, but because lectures always highlight my day, but still you need to have a lunch to survive. So would it be okay that we're gonna go over this study, this story about Benowitz-Hartenberg, then very small break, and then we're gonna close a bit before, a little bit before the noon. It's okay. Sounds okay. Okay, here is my robotic system. Consists of 2 arms, and actually you see that this is nothing but a double pendulum. not too complicated robotic system. So this consists of two bodies, okay? So what I need to do is that I need to create the table that there are 2 rows for each of the bodies, the body 1, body 2, and each of the rows, they have 4 columns. And these 4 columns are, how is this DH parameters for body 1, how is the DH parameters for body 2. And once I do that, and once I do the substitution, then my kinematics is done. My kinematics is made. All right? So it goes like this. So the first parameter, which is the length of the body, how much is that? First body, and let's focus on this row only. This row here. Okay, so length of the body is this, L1. What about alpha? How much they are twisted? Remember this twisting thing. Not twisted at all, because they are having the same orientation and this end and this end. This is 0. This distance, like how much they are separated in this direction. They are not separated in this direction, so that too is 0. And then comes initial configuration angle theta. So it's going to be this one here. All right? Same. So this is another relative thing. So this is something that I did not mention clearly. But these are always relative coordinates with respect to your body before you. So this is how you're describing these parameters. Again, there's a length. This is 0. This is 0. This is describing this relative angle here between the body 1 and 2. Body 1 and 2. This is my first transformation matrix. This is my second transformation matrix. This corresponds body 1. This corresponds body 2. You do the multiplication. This is your kinematics. This tells you the orientation. This tells your location. Kinematics done. Now, if you suspect that there is a singularity problem, what you can do then is that you can take your symbolic math tool and you can differentiate this 4x4 matrix with respect to your angles. This is going to be your Jacobian. And then you can compute the determinant of your Jacobian. And that tells you quite a bit about how healthy is your mechanism, your robotic system, to be more specific. Okay, that's what it is. All right, then now I redo the same by using my multi-body thing. So I'm using relative coordinates. I'm using this equation. But this time it's a relative coordinate. So I need to use this one rotation after another technique. I'm not going to go into details here because you guys are going to get the slides later. And if you want to familiarize yourself with the detail, you can do that a little later. And I get the same result, same end configuration. Okay, that's how it works. Now, how much time you need to recover? 5 minutes. 5 minutes. Okay, 5 minutes. And then we're going to close, again, we can close 10 to the noon, or even maybe earlier than that. Okay, so 5 minutes. Okay, let me mute myself.
Do you want to mute first?
Sure. Is it this? I think it is.
present in the next simulation, next tutorial course.
Yeah.
Okay, because this time I missed it, but from the next time I'll be there. We can discuss it with the
Thank you very much.
Okay, so we are done. We are done with the break, so we can continue. Can you check if the audio is back on?
Okay.
I think it should be okay. I made everything like it was a while ago, so it's okay. Good. Okay. Okay, guys. Yeah, I see. You know, I realize that I'm not as fast as I would like to be, so I'm running a little behind of my original plan. Anyway, so I'm gonna do this 3D multi-body dynamics fastly, because pretty much the information that I wanted to give it to you is this one. You know, that if you have 3 rotational parameters, regardless of your choice of rotational parameters, and once you differentiate those with respect to time, they are not equal than angular velocities. And that's a little bit of, not a little bit of headache, but it's a major headache. And this is something that requires a special attention. It requires a special attention, which typically is something that the users are not so much familiar with. And why this is a big deal? It's a big deal because, you know, to keep certain parameters of the model, it makes a lot of sense to use a local body reference coordinate system. So it makes sense to give a like inertia tensor, which is properties of your, you know, how much is resisting the rotations. It makes sense to give that with respect to your body reference coordinate system, because otherwise it can be complicated. And this is something that you need to take this mismatch into account. So we're gonna shortly explain this mismatch, this problem to you, and that's it. We're gonna leave it, and we're gonna move on to flexible multi-body dynamics, which is entirely, completely another field, because then assumption we have used very extensively so far, which is that the particles cannot move relatively with respect to each other, is no longer valid, because in the deformable bodies, they can. They can. Think about this end and this end. This is no longer constant because of the deformation. The length here to here is changing as a function of time or a function of a deformation. And that's a significant thing. That's going to change everything we have learned so far. And that's where we're going to make a use of the method called finite element method. Okay. Very, very good. Okay, so 3D multi-body dynamics, and these are there's a one question only. How inertia tensor can be related to acceleration of rotational generalized rotational coordinates. Okay, this is a little bit too many times rotational there. I realize that, but that's my question. So how it can be related, and it comes from this relation, how you related your angular velocity and rotational parameters. That's where it's coming from. Okay. All right, so this is a kind of like a little bit of warming up. So once we are looking at the velocity of a particle, so it can be taken or it can be obtained by differentiating your position or position of the particle. Once you differentiate that with respect to time. Once you do that, you will get the 3 components. One of them is going to be equal to 0. One that will be equal to 0, it's going to be this one here in the middle. And why is that? Because the vector u bar is constant if the body is rigid. So if the body cannot deform, vector u bar is constant. So once you differentiate vector u bar with respect to time, it disappears. What is left is translational velocity as something that comes when you differentiate your angular, 3x3 rotation matrix once with respect to time. When you do so, you will get this angular velocity. Now the angular velocity can be with respect to your global coordinate system, which is denoted here as a omega tilde. So it's a skew symmetric form of the vector. If this is without the bar, it's with the reference coordinate system. And if it is with bar, it is with respect to body reference coordinate system. Difference is this. If the angular velocity is expressed with respect to this body reference coordinate system or with respect to reference coordinate system, that's the difference. So it's like, is it relative body reference coordinate system or is it with this reference coordinate system, often called as a global coordinate system? So that's the difference. All right, so now this is how this velocity can be expressed. And now things becomes to be complicated because if you look at this velocity expression, we have not explicitly be able to express this by using derivatives of rotational parameters because we have angular velocity, but not what we wanted because we would like to express everything, position, velocity, acceleration, using all the time same parameters, which is these generalized coordinates. And it's not here, at least not explicitly here. And we need to do something about it. Something we can do is, first of all, the observation is this, what I just explained. Angular velocity vector is never same than time derivative of angular parameters. And it's clear if you use 4 parameters, they cannot be same because mismatching in the dimension. They cannot. That's obvious. But even when you use the 3 parameters, they still cannot. They still cannot. They need to be related. And the way they can be related is it's called something like G matrix. G matrix is coming from the kinematics, is describing how you can relate those 2 things together. And this is the answer to the question that was in our first slide, how you can express the inertia tensor using any generalized coordinates. Answer is with help of G matrix. G matrix depends what is that you wanted to relate, what is that you wanted to combine together. You want to combine 4 parameters to angular velocity or 3 parameters to angular velocity. But here is an important thing. Never, even when you use a 3 angular parameters, never assume that it's same than angular velocities because they are not. They are not. They can be related with help of G matrix, and that's pretty much what I wanted you to know. How they look if you're using Euler angles with the rotation sequence that we've been discussing before. G matrix look like this. If you take a close look about the G matrix is actually rotation axis. Rotation axis. Because when you look at the first column, that obviously is a z axis, z coordinate axis. And if the angle phi, if the angle phi is equal to 0, second one is going to be x-axis. If the first rotation and second rotation are equal to 0, third one is going to be again z-axis. So that's where they're coming from. Now, where they're coming in a general case, you cannot even tell because they are so case dependent, depending what you wanted to do. But my story is this, once you have the G, then you can do the relation. And then you can explicitly express variables, generalized coordinates in your velocities. You can do the same for acceleration. And now it becomes to be possible to relate whatever computation method you're using, whatever parameters you're using, to inertia tensor that is expressed by using your body reference coordinate system. You got the point? Okay, let me summarize this briefly. Because of physics, angular, or let's say, I don't know, because of this planet, because of the Earth, because of, I don't know where this is coming from, because of the way we describe it, the kinematics. Angular velocity is not the same that time derivatives of rotational parameters, but they can be related, they can be linked. And the way we're going to link them is with help of the G matrix. And this is a necessary step to do, because otherwise our kinematics, which is this one here, is expressed without knowing what are the generalized coordinates, or velocity of generalized coordinates, because that's the one we wanted to solve. All the time we wanted to solve the unknowns, which are generalized coordinates. Okay, I said that I'm going to be fast here. Now, This is what the T matrix looks like. So now with help of T matrix, I can relate my generalized coordinates and angular velocities. And now we're going to go back to the in-class quiz. My in-class quiz is this. So let me see if you guys have enough information to answer this. Matrix T is important because it couples local and global coordinates. It couples angular velocity vector and time derivatives of generalized coordinates because it describes inertia properties of body, couples global and generalized coordinates. I don't know, guys. Do you have enough information to answer this question? You know what's the correct answer? Hey, why don't we do the following? I'm going to put this on, but before you entering your answer, you need to discuss at least with 3 fellow students. So you are not allowed to answer or enter your answer before communicating with the 3 members of this class. So you need to communicate. You need to make an agreement, because otherwise we are not going to have a great success rate. Okay, so here's are the online participants able to see this? Can you check this?
Yeah, like there has been no comments.
Okay, can they? But how it look in YouTube? Can they see this screen?
Yes, not this one.
Not this one.
They still see the slides.
Slides. Okay, so I need to. Okay, so what about this when I do like this? Yeah, now they see it. Right.
Yes.
Now they see it. Okay, yeah, let's first close this one. So we have the first in-class quiz. How is going to be the success rate here? How much is how many percentage of the students will get this correct? 90.
90.
No, it's 100. Of course it's 100 because this is exactly the same question that was a week ago. So a week ago. So we are testing here the progress of learning. So if the percentage is lower than it was a week ago, we need to stop this. We need to not to give lectures anymore because obviously we're moving in the wrong direction. Are we moving in a right or wrong direction?
I say 5 people would speak to the wrong.
Why? 5. Okay. Okay. So I'm saying 100%. You guys are saying something else.
90 something.
Oh. Okay, this has nothing to do with if the body is rigid or not. Nothing whatsoever. And the other options were not used. And I'm happy about this. That's what makes me super happy. This week, no one is saying that the body can rotate in 4 different ways, which is a great progress. It's a fantastic progress. I don't know who was it, but the last week somebody was saying that, yeah, if you take a time space into account, then maybe, but we are here in this planet, we are not considering this thing. This is like back in a future movie business. And here we are more in the reality, so that's what it is. Okay, we're moving on to the next one. Okay, why is the T matrix T is important? Because it doing what? And again, don't answer right now, but first communicate. Make an agreement. Make an agreement. Okay, you guys are absolutely sure what is the correct answer? Okay, then you can go. If you're absolutely convinced that you know the correct answer, then you can enter your answer. And I'm going to take myself back here. This one. You good? Not yet. Okay, what about the back row? What about Team Finland? Team Finland is convinced. Team Finland is having can-do attitude. Nice, very nice. What is another team in the back row? What's your rest of the world? Okay, so this becomes to be interesting. So team rest of the world is saying yes, we know what is the correct answer. Okay, fantastic. Rest of the world. I like that. So it's the Finland against the rest of the world. Well, that's a challenge. Okay, no pressure to Team Finland at all. No pressure. But it's our reputation, Finnish reputation in the line. So it's a big deal. Okay, all right, you guys done? Can we move forward? I'm going to get back to these results momentarily. Now let's look at something a little different, and then we're going to close the case. Okay.
It hasn't, you haven't changed it on the slides for the online.
Oh, yeah, of course, of course. But how many answers we got? So is it still like 9 only? No, we got 50. Last time it's a 55. But I'm expecting some of you guys are giving up. So I'm going to take a look at this.
It's going up.
51. Okay. Okay, I'm gonna close this one. Okay, success rate. I'm saying 70%. 80. Okay, yeah, 80. But is it not going to be 100? Definitely not 100. Not 100. But is it going to be, okay, so here it is. So let's take a look. Okay. Oh my God. Wow. Oh, I don't know what to say here, because this is a seriously complicated question. I was so sure that the success rate is low. Like I was thinking 70 is the absolute max. Absolute max. It cannot be any higher than that. You guys have the WhatsApp team, or you don't? You still don't have this WhatsApp communication?
It's communication between us.
Communication. Oh, is it called classical communication? Oh my God. I am happy, very happy. I'm not going to call Rector this time, because last time when I called him, I saw him in a corridor. He said, "I don't know about you, Aki. So I don't, maybe you need to have a rest or something." And okay, I'm not going to call you anymore. Okay. Those of you that was in a class in a fall semester, so we actually called the rector when we scored 100%. And he was like, "Why is that you calling me?" And I said, "I want to show like how good students I have here." Okay, here, this is it. Now I'm gonna close this story. So I would like you to memorize the T matrix. The T matrix is a magic. I'm gonna make a short revisit to the T matrix next week. And why? Because I still need to make this relation to inertia tensor. But rest from this relation is easy. What you need to understand is what we just described. So it combines angular velocity vector to time derivatives of generalized coordinates. That's what it's doing for us. Once you understand that, that's it. That's pretty much all you need to understand. Now, next week we're going to revisit and we're going to look a little bit about what that represents for us in terms of inertia tensor. But now comes something a little different. So so I need to do this. I need to hide. Yep. Yes. Okay, we're going to move on to flexible bodies. Now, there's a few things that I would like you to be aware of the flexible bodies. This is going to be, there are 2 more in-class quizzes. I don't know if we really have a time to do so, but I hope we do. Okay. First thing, important to understand. Flexibility is needed to increase accuracy of the model. Sometimes the flexibility of the body is so significant that if you make an assumption about the rigid bodies, the results are going to be poor representation of reality. They are not having the close relation to reality. So it's a clear way to increase the quality and accuracy of your model, increasing the description of flexibility. But here comes the difficult thing. They've been an attempts, serious attempts to make some kind of rule of thumb when the flexibility needs to be described. So when is that the flexibility is significant enough that you should take that into account? And that's impossible to say. There's no way to say. Sometimes it say that if you can see from your bare eyes that the structure is slender. Yeah, but that's not enough because it needs to be highly loaded to make that deformation to be significant. Sometimes it is, okay, if the lowest natural frequency is within the certain range, that's another reason that you need to take the flexibility into account. But there are always exceptions. Always you can set these rules, but then there's an exception of exception. Honestly, there's no way to know that. The only way to know it is the model structures as a flexible bodies to see whether or not that makes an effect. And this is where you can show off, because you can create the method of your own to tell your fellow workers whether or not the body needs to be described as a flexible body. So you can do like measurement like this. And then you can tell, okay, tell me what is the wind today? How is the position of sun? And then, yes, it needs to be modeled as a flexible body. But as a general rule, there's no rule. You cannot know that. There's no way to know it. It's just based on your engineering sense. Common sense, if you may. Engineering sense may be better. Here's my next in-class quiz. When deformation needs to be accounted in multi-body application? When large force is applied to system, when the natural frequency is low, when slender, thin structures are considered, there's no general rule to make this decision. Okay, and I'm going to take myself to this one. And the next one is on. We're going to take a look at this. And then I'm going to tell you one more story, and then we're going to, this one. Okay, take a look at the options. And you're welcome to communicate again. And I think as soon as I see that you are not communicating anymore, then I'm going to move forward. Okay, can I go? You guys are done. All right, so I'm gonna go and I'm gonna get back to this momentarily. All right, this is something that I explained earlier. So field of flexible multi-body dynamics means that the flexibility of the body is accounted, is taken into account. There are two families within this one framework. And these two families are different in terms of how you are taking deformation into account. Is it that you take a large deformation into account, or are you limiting yourself to small deformation? And this all becomes how you relate it to displacement and strain. I need to apologize that I'm unable to make a drawings, but the displacement is like how much each of the point of a cantilever beam has moved from its original configuration. That's what the displacement is about. And strain is that how much the material is expressing strain because of this displacement. This relation can be linear, which is very common assumption, or it can be nonlinear. They have completely different way of how things are described. Because if you're describing this relation to be linear, it means that like second order deformation is not accounted. Second order deformation in the case of cantilever beam means that if you look at the free end of the cantilever beam, and when you're loading the free end, the loading end stays in a loading line, which is okay if the deformation is small. And it becomes to be very unnatural if the deformation is large, because the deformation then would be something like, again, now it's going to be a great benefit for people here in a class. What's up with these ones? Okay. No benefit. One more attempt. Okay. Like when you have the free end, if it's going to be deformation like this is not happening in a reality. This is not the case. So in reality, it will be something like this. This you can take into account only if you are assuming the relation between the displacement and strain to be nonlinear. This having the very severe consequences the way the things are described mathematically. And these are two different families. That's why it's like a large deformation family and small deformation family within the family of flexible multibody dynamics. Okay, we're going to focus on small deformations. That's where the classical finite element methods are focusing on too. Okay, so that's how it is. And you see this is what the animation will look last year too. So there are two cantilever beams, one with an assumption of linear strain displacement relation, another one with a nonlinear, and obviously the one where the pendulum at the end of the cantilever beam is going in all possible direction is the one where the nonlinearity is taken into account. Okay, so that's how it is. Now I'm going to tell you lamp mass approach, and one more time I'm going to emphasize something that is called mathematically stiff problem. Mathematically stiff problem, and then we're going to go to have lunch. Okay, lamp mass approach is a way to describe the flexibility, which is very, like, let me say, like, not too sophisticated way. Not too sophisticated because this is the method that is based on the assumption that a rigid body is described by a series of rigid bodies that are connected together via springs. That's like almost like an application, and it is actually an application of rigid bodies. So if I have original beam-like body, now instead of using one rigid body, I'm going to take a multiple rigid bodies, each of them connected together using spring elements. Okay, this is a nice way to go, but comes with this problem of numerical stiffness. And numerical stiffness is not that something is stiff, physically stiff. It's almost the same thing like this Kimball locking is not mechanical lock. And the numerical stiffness is not something is very rigid. But it means that this easily leads to the models where you have high frequencies and low frequencies in the same model. And this is always numerically something that you want to avoid as much as you can. And the reason is this. When you look at the response of the system where there is a high frequencies and low frequencies, the overall behavior may look like this, that this beam is bending like this. But when you have a very close look about the behavior, the system might recognize that there is a very small vibration with very small amplitude, insignificant amplitude. For example, in axial direction. The system is moving in axial direction insignificant way. But because it recognizes that there is a movement some kind in this direction too, it is kind of getting alert. Hey, oh my God, there's something going on with this direction. So let me make my time step to be small enough that I can see what's going on in this direction, because integrators are not able to differentiate, generally speaking, what's significant and what is less significant. They do their best job to take everything into account, including the ones that you don't care at all. And this is something that slows down the computation because it's thinking that, okay, this very insignificant vibration in a transverse direction is something that you guys are interested in. And typically you're not. And you can get rid of this by selecting the models where the frequency is more or less in the same region. It doesn't matter if it is high or low, because the integrators can tune themselves to take high frequency into account if they're in the same frequency, and they can take the small frequency into account. But if there's a combination of both, that's what things becomes to be complicated, and that slows down your computing. I'm going to make an additional drawing to that next week, but that's something that is a problem when you use this method. You see that because the bending, when you have these lump masses, actually will have somewhat low frequency. But because it can also move axial direction. There's going to be quite high frequency related to that. Or let's say neighboring two masses are moving relatively with respect to each other, very high frequency. This is something that you want to avoid as much as you can, because otherwise computational efficiency is going to be low. All right, so my last in-class quiz is this. So there's going to be a bit more stories about how this behaves, some animation examples, computationally expensive because of the stiff system, can be applied for beam-like structures only. Material damping is somewhat simple. easy to implement, easy to use, simple theory. And my last in-class quiz is this: what numerically stiff system means. That the system contains low and high frequencies, that the system contains high frequencies, that all bodies are assumed to be rigid, that some of the bodies are assumed to be flexible. One only is correct. Okay, and I'm going to take myself here. Okay, so again, I need to make an adjustment to my, it was a window capture, this I think, right? No, this one.
The fourth one. Yes.
Fourth, this one.
No, the one, yes.
Yeah, okay, here it is. Okay, success rate of this is what? Okay, so we got all the answers already, so it's a 52 answers. So when, okay, answer is 88. It's okay, because I'm still happy because the last one was so difficult that you guys did so well. So I'm not disappointed at all. What about the last one? The last one is this. Numerically stiff means system contains high and low frequencies. That the system contains high frequencies, that all bodies are assumed to be rigid, that some of the bodies are assumed to be flexible. And again, it's all right to communicate. Once you're done, you are good to go to have a lunch. So did you have a lunch already? No. Yeah, with me all the time. Okay, so I got 36 answers, 37 now. I'm at 40. I'm missing 8 answers, I think. Like last time it's a 52. No, 8 is missing. So it could be a little lower. So if as soon as I get more than 50, then I'm gonna close this and rush myself to have a lunch. Okay, so okay, are you guys done? You entered your answer?
5 more to go to be faster.
Okay, 3 more to go. Okay, next week is all about finite settlement method. Fantastic method. And it really would be nice if you guys, if you are familiar with the finite settlement method, it would be nice if you can argue against me. So because I would like you to be like, no, this is not the way that I have learned the method. So what about this and that? I would be more than happy to communicate, more than happy if you have any doubts, any criticism, like, is it really like that? Okay, one more answer and then I'm gonna close this and then we're gonna go to have a lunch. By the way, I think my voice quality is better than it was last year because of this new mic system. So I'm loud and clear.
You're on your way to teach the professorship and becoming a blogger.
Yeah, I felt the same. Felt the same. Okay, one more answer, please, so then we can go. One more. You all done? You all done? So why can't we? Oh, there it is. Okay, now it is. Success rate is what? 100. No 100? Not 100. It's 100. Yes, it is 100. 80. 90. Okay, high frequencies, Richard. Okay, this is it. Okay, so let's close the recording.